Hello everyone, good morning. Welcome to Ganit. I am making this video really early today. Actually, sorry for any kind of trouble because I will be traveling today, so probably I'll not get time today and tomorrow. So, as you can all see, we are going to discuss the infamous circles. I mean, this is a topic really mostly not liked by anyone. That does not include me. I love this chapter. There are a few topics in maths which I really like more than the others. Circles is one of them. Trigonometry is one of them. The next topic that we are going to do after circles is trigonometry. But circles is super important from the perspective of grade ninth as well as 10th. Please know that when you do circles in ninth grade, you may have a different set of circle theorems in grade 10th. But trust me on this, almost 70% of the questions asked in 10th grade board exams also, they have not really anything much to do with the grade 10th theorems. A lot of grade ninth theorems find use in circles. So circles, let's start without further delay. First we are going to learn about a few definitions related to circles. What is a chord? This is a chord, okay? So if you draw a line inside the circle, and both its endpoints are on the circumference, on the boundary of the circle. It's known as the chord. You can guess that the longest chord of the circle would be the diameter, right? There can't be any bigger chord than that. I'm sure you are already familiar with radius. So in this chapter, radius is a very crucial thing. Of course, the name of the chapter is circle, so you might think, yeah, what are you blabbering about? But radius has very different role to play in this topic. You will see once we start solving the questions. You will see what I mean by that. There are a few other things, like suppose you have a circle and you pick a circular part of it. Let's just say your center is here, and you pick, let's just say, A, B, C. I'm not talking about a line, I'm just talking about that curved part ABC. So we call it arc ABC. We represent ABC arc with that symbol above it. Okay. So let's start with the theorems now. Theorems in circles are majorly categorized with chord properties and angle properties. Angle properties also include the arc properties. We will come to that later. First, we will try and focus more on the chord properties. Very basic in nature, but very important to observe the diagram correctly. Like we have seen in midpoint and intercept theorem 2, the how you decode the diagram almost decides are you going to get the question quickly or not. You may still get the question correctly, but how much time you're going to spend on it, I am not too sure about it. So learning a theorem, that's one thing, but learning a theorem and then predicting it in a question, or catching it up in a question, spotting it in a question, those are the important skills to have. So let's see the first property. So we have a chord and we drop a perpendicular on it from the center. So it divides the chord into two equal halves. Okay. So this is the diagram of the theorem. What would be the diagram of a question? We'll talk about this, but let me explain the theorem first. So if we have center at O and the chord is AB, so what we need to understand it, if AC is perpendicular, sorry, my bad. OC is perpendicular to AB. Remember, the sign does not indicate perpendicular bisector. It just indicates perpendicular. It bisects later on because of the theorem. That's another story. But please don't make any judgments based on this. You may see this sign a lot of other places too, in other chapters too, in geometry. This means perpendicular. Please remember, it does not mean perpendicular bisector. Okay. All right. So OC is perpendicular to AB, then AC is equals to BC. Okay. So what is the given information for you? This is given. This will be told that we are dropping a perpendicular on the chord, and this is your result. Okay, but I would be not fair if I don't complete this diagram. In the questions, for all practical purposes, you are going to have this as your radius. Please remember, guys, when you see a question in circles and it says the radius of the circle is 5 centimeter or whatever, please do not start marking this as your radius or this as your radius or this. No, it's of no use. This has to be a radius, and if you have not guessed it till now, let me tell you, for all practical purposes, for all question related purposes, you're going to use Pythagoras theorem in this triangle because it's a right angle triangle, and hence we need the radius exactly where we have got. If you draw the radius in some random position in some random place, then you're not going to get Pythagoras theorem into the game, and that's where the problem will begin. So, knowing chord properties is something different, but knowing how to solve a question using it, it's a totally different ball game. I hope you understood this first theorem. Okay. Now, every theorem has a converse of it. So, when we say Pythagoras theorem is applicable in a right angle triangle, for instance, we also use Pythagoras theorem to show that the triangle is right angled. Correct? So theorem and its converse are completely related. Okay, they are true. Both of them will be true. If a theorem is true, its converse has to be true. If you draw a set of parallel lines, suppose, you'll see alternate interior angles as equal. But if the lines were not parallel, and these angles were still equal, you could use those angles to tell that the lines are parallel. So parallel lines generate alternate interior angles, but alternate interior angles also help in generating parallel lines. That's the difference between a theorem and its converse. So when you talk about the theorem, you should know the converse of the theorem is also valid, it's also true, it holds value. Okay, so the converse of the theorem would be, I have a circle, I still have the same diagram, but this time around, I have AC is equals to BC. I don't have the perpendicular. So what will be the converse of theorem? What will be the converse of theorem's statement? The statement will be if AC is equals to BC. That means if a line from the center would have bisected a chord into two equal parts, bisecting is anyway two equal parts. So in that case, OC would have been perpendicular to AB. So if you notice here, what was the result became your given condition, and what was given actually became your result. Okay, so that's the difference between a theorem and its converse. I hope you have understood this. So, usually in your textbooks, in your school class, they might explain this to you as two separate theorems. We're not going to do anything like that because the goal is to make you understand the concept easily, not to scare you off. And I'm not going to load you with theorems. I'm not going to load you with statements and all. Understand the theorem from here, understand it in easier terms. For statements, you have textbooks, you have school teachers, they will definitely load you with that. Not my job. Okay, so let's move to the next theorem. So theorem number 2, again chord properties. So if I have a circle and I have two chords inside the same circle, okay, let me join this. Sorry. So I have two chords this time in this theorem, and they are equal to each other. This is center O. Okay. So what does the theorem say? Theorem says equal chords. I just want to give you a glimpse of what your textbook will say, what your school teacher would say. But so I just want to give you a glimpse, and then I'll tell you how I break and decode this question as a student of maths. Please understand this. I have all my life these things have helped me. These small things have helped me in solving questions, and trust me on this. I have been solving mathematics for quite some time now. It's been almost 20 years that I have only studied mathematics as a subject, never anything else. So understanding the theorem from the textbook in their own language and then breaking it down into something which makes me help, makes me solve the question easily. I think that's what maths is all about. So how your textbook would say, equal chords subtend. This word confuses a lot of students. I'll explain that word. Equal chords subtend equal angle at the center. Now, my version of this theorem, the way I understood it better when I was a student, and I loved every bit of it, is this. So, if AB is equals to CD, then angle AOB is equals to angle COD. Subtend is nothing but making of an angle. So if you see the chord AB, both ends of AB are being joined and coming together at center O. Subtending means you converge at a point, you go and meet at a point, right? And that's how you create the angle. So if AB is equals to CD, that's a given information. This is my result. So no prizes for guessing the converse of this theorem, which would be in a similar kind of diagram. But I think by now you can guess that this time around, the chords are not given as equal. Remember, what's given becomes your result. What's result becomes your given information. Okay. So I have the chords A, B, and CD. And the theorem goes on like, if the angles made or subtended by two chords are equal at the center, then those two chords will be equal to each other. Okay, so just the reverse of the theorem. So practically put, if angle AOB is equals to angle COD, that's given this time around, then chord AB will be equals to chord CD. That will be your result. So this is theorem 2 and this is its converse. So we have seen 4 theorems as per the textbook right now. Theorem 1, 2, 3, 4. I mean, for us, it is 2 theorems and their respective converse. Okay. Now, moving to the next one. So, this theorem is again based on equal chords. So, suppose you have two chords equal to each other, and this is your center. So, let's just say A, B, C, D, point O, this is P, this is Q. So, if two chords are equal to each other in length, AB is equals to CD, then OP will be equals to OQ. Their respective perpendicular distance from the center will be equal. So AB is equals to CD is a given information to you, and this is your result. Please also understand that if you're thinking about theorem number 1 in this instance, you are absolutely right. Okay, I have drawn a chord, I have drawn a perpendicular. So you are well within your rights to think about theorem number 1. So in such situations, if the question goes on to ask you the radius, you have to use theorem 1 as well. So this is theorem number 3 based on equal chords. Okay, and obviously you can easily guess what would the converse of the theorem look like with a very similar diagram, but this time around we will not mention that the chords are equal. This time we will mention that their distances are equal. So the question says, the theorem says, my bad, OP is equals to OQ. That's given to us. Okay, then AB would become equals to CD, and that's your result. Okay, so of course this diagram looks very similar. If we just remove a complete chord and the perpendicular, it's just theorem number 1, right? So theorem number 3 can be interpreted like this, and remember there is always an element of theorem number 1 in this theorem. Okay, so equal chords have these two properties. In the next set of lectures, we are going to also follow how equal chords and equal arcs are related to each other. We are also going to learn about how equal arcs make equal angles, and some angle related properties too. For now, you can go through this much and solve a few questions if you want. There will be more videos on circles. Till then, I'll see you. Okay, thank you. Bye bye.